All right, I think we can get started. We have a quorum here. Good morning, good afternoon, everyone. It's our great pleasure to invite Xiaotao Shen to give us a talk here. Dr. Shen is a postdoctoral fellow at Stanford University, and he's currently working with Dr. Snyder. Before that, he completed his PhD in Bioinformatics and Metabolomics from the Chinese Academy of Sciences and got his bachelor's in biotechnology from the Inner Mongolia University. Most recently, Dr. Shen received the Stanford honor for rigor and reproducibility in research, which is fantastic. So broadly speaking, Dr. Shen's research interests focus on bioinformatics algorithms, software development for multi-omic data, and more particularly their application in precision medicine. So without further ado, Dr. Shen, please take it away. We're looking forward to your talk today and your e-visit. Thank you.
Yes, thank you. Thank you so much for the very nice introduction. Let me share my screen. Okay, so can you see my slides? Okay, yeah, thank you so much. Yeah, okay. Okay, thank you so much for your very nice introduction, and thank you everyone for coming. My name is Xiaotao Shen, and I'm a postdoctor at Stanford School of Medicine. And I'm so happy to have this opportunity to present my work with you. And the title of my presentation today is, let's get a letter, sorry. Title is Bioinformatics, Algorithm Development for Mass Spectrometry Data and its Application to Precision Medicine. Okay, so there are 4 parts in my presentation today. The first part, I want to give a very brief introduction about my research background. And the second part is about the bioinformatics algorithm development for mass spectrum data. And third part is about how to use mass spectrometry for the precision medicine and biological question studies. And the last part, I want to give a brief introduction about my future plans. Okay, so let's get started from the first part, the background. So I think most of the audience may hear something about the metabolomics, but some of you may don't know the metabolomics very well. So here I will give a brief introduction about the metabolomics. So first, what is metabolomics? As we all know, there are a lot of biological molecules in our body, and such as DNA, RNA, protein, metabolites. And all those molecules can reflect our physical and pathology. And systematic studies for different kinds of molecules generate different omics. For example, DNA, we get the genomics, RNA, we study the transcriptomics, and protein, we study the proteomics, and studies all of the metabolite in the human body, we get the metabolomics. And the system biology study all the molecules and their interaction in the bodies. So according to the central dogma of molecular biology, we know that the flow of the genetic information is from DNA to RNA and from RNA to protein. And we all know that the proteins can be used as atomized to catalyze the reactions between the different metabolites. So if genomics and the transcriptomics tell us what can happen, so the proteomics tell us what may happen, and the metabolomics can tell us what has happened and what is happening. So the metabolomics is closer to the phenotype compared to the other omics. This is why we also say that the metabolomics is the most downstream of the system biology. Next, why do we need to do the metabolomics, or what metabolomics can help us in our studies? So metabolomics is the large-scale studies of all the metabolites in our body. And a lot of factors can affect the metabolites in the human body, including genetics and environmental factors, such as sex, aging, food, exercise, diseases, drug, and so on. And the affections can be reflected by the metabolic data from the human body. So this means that through the study of the metabolic data, we can know the human health status and what affect the human health status. So the application of metabolomics can be divided into 2 parts. The first part is biological mechanism studies, and the second part is biomarker discovery and disease diagnosis. So now we know that metabolomics is very important and very super powerful for biological and precision medicine studies. So how to do metabolomics? And this question can also be asked as how can we measure all the metabolites in the biological samples? The most common and popular technology for metabolomics, like this figure shows, is LCMS, is liquid chromatography mass spectrometry. And this figure just a brief illustrations of the time of flight of mass spectrometry. And briefly, the metabolites get charged in the aerosols, and for example, the hydrogen or the sodium. And after getting the charges, the metabolites can be detected by detectors and have different time of flight. Based on the time of flight, we can calculate the accurate mass of different metabolites. So finally, for all the metabolites, the mass spectrometry can give a signal like this figure shows. We call it metabolic feature or metabolic peak. And unique metabolic feature is defined by the accurate mass, namely mass to charge ratio here, reading time, and we call it RT and intensity. So after getting the mass spectral raw data, how do we process it? So this figure just showed a very common and widely used workflow of LC-MS metabolic data processing analysis. After we get that mass spectral raw data, we need to do the raw data processing, and then we get the feature table or the peak table. And we also need to do the data cleaning to remove the batch factor or input the missed values. And what is important that for the data processing is the metabolite annotation, because we need to do the metabolite annotation, we know what the features they are. And then we can do the statistical analysis for the biomarker discovery or the biological interpretation. So there are a lot of challenges of LC-MS metabolomics, especially data processing and analysis. Like this figure shows, I just, in the past few years, I developed several tools to improve the processing of metabolomics data in this field. Like this figure shows, for the first one. So let's see the first one in that the comprehensive workflow. There's no comprehensive workflow and reproduced workflow for LC-MS data processing. So this is why I developed this method. So let's jump into the second part of the bioinformatics tools developed for the mass spectrometry data. The first one is the comprehensive computational framework for LC-MS based metabolomics data. So actually, there's a lot of tools have been developed in this field for metabolomics data processing and analysis, like this figure shows. And all the tools can be divided into three classes. The first class is commercial tools, and we know that the commercial tools are user friendly, but most of the tools, they are not free. They are very expensive and only work on associated instruments. For example, the software from Thermo Fisher can only be used for the data from the Thermo Fisher instrument. And the second class of the tools is online or GUI tools. They also user friendly, but they can't, because most of the tools only support the Windows operating system, meaning that can't take advantage of the cluster and the server condition resource. And the third class of the tools is open source tools. And so, these cross-platform utilities, it can be installed on different operating systems. But most of the tools, they only typically follow limited parts of the whole bioinformatics flow. So this is why I want to develop a comprehensive computing framework for LC-MS metabolomics data processing analysis. I call it TenMass. To overcome the limitations of existing tools, we have several concepts of design of TenMass. The first one is cross-platform utility. TenMass is developed using the R language in that this package or this tool can be installed on all operating platforms, for example, Windows, Linux, or the Macs. So the technical concept is uniformity, shareability, traceability, and reproducibility. TenMass is modular and object-oriented workflow. This means that for each step of the whole workflow, one package will be developed, and the object will be processed by functions in different packages, and all the process steps and parameters will be recorded in the object. This is very important to trace and reproduce the processing and analysis. So the third concept is the flexibility and extensibility. The data structure object in TenMass can be converted to data structures of other softwares. So it means that the users can easily combine TenMass with other software for data processing and analysis. In addition, we can easily develop the new tools based on the TenMass. So this figure just shows a mass dataset class in the TenMass. The data structure, in the TenMass. So it's a core of the TenMass processing analysis. It is an object that combines all the data and the information of metabolomics data into one single dataset. As this figure shows, it contains experiment data, sample information, and wearable information. And we know for the mass spectrum data, we also have the MS spectra or the MS2 spectra for the features. So we can also include the MS2 spectra in the class. And what's important that the dataset in mass dataset class are automatically synchronous, and they support the popular tools from other packages because we know there's a lot of people have developed a lot of powerful tools in R. So we can just use these powerful tools to process a TenMass object mass dataset here. So let's see the workflow again. The package in TenMass can be used to do the whole workflow of the data processing analysis. For example, we have the mass converter. This package can be used to convert the different format of the mass spec raw data. And we have the mass processor that can be used to do the raw data processing of the mass spec raw data. And we have the mass cleaner can be used to do the data cleaning or the data cleaning steps for the mass mouse data. For example, the mismodification and batch file remove. And we also have meta ID package can be used to do the meta annotation. To help the users to learn how to use TenMass, we also developed or provided very detailed help documents and tutorials in the website of TenMass. And for each package in TenMass, because TenMass is not one package, it contains different packages. So for each one package in TenMass, we also have a website for it. So if the users only need one package for their data processing or analysis, they can just open the website of this package and learn how to use it. So let's see the workflow again. We can see that Metabolic annotation is a critical step in the whole workflow. It is that transfer the chemical information because from the mass spec raw data, we just get the chemical information. So it's a critical step to convert or transfer the chemical information to biological information. However, as I mentioned about the Metabolic annotation, is very difficult. So, Nature Medicine journal just selected the method towards 2022, I think maybe 1 or 2 months ago. And, you can see that noting unknown metabolites is one of them. And I quote one paragraph from the Nature Medicine: comprehensive annotation of unknown metabolite remains a challenge. So why the metabolite annotation is so difficult? We know that the DNA sequence contains just 4 bases, namely A, T, C, G. And the proteins contains only 20 amino acids. So it is very easy for DNA and proteins annotation. But for the metabolites, it's very small and has no specific units. This is why metabolites annotation is so difficult compared to DNA and protein. The most widely used and accepted method for metabolic annotation now is based on the MS spectrum. And briefly, the metabolites are broken into different fragments, ions with different mass. And then the fragments of the metabolite just generated the MS spectrum or MS2 spectrum here. So we can get the MS spectrum libraries of metabolite standards. So we just match the experimental and standard MS spectrum for notation. Because the high sensitivity of the mass spectrometry, we can always get more than 10,000 metabolic features from the biological samples now. And however, only around 10% of the features can be annotated as metabolites, and around 90% of the features have no annotated result. This is because we can't have all the metabolite standards MS spectrum. So it means that the new strategy is required for metabolite annotations for untargeted metabolic state. So next, I want to, I just developed a new method to overcome these limitations for the metabolic data. And I create a metabolic reaction network based on metabolic annotation. So the motivation is like this figure shows. We know that all the metabolites in our bodies are linked by metabolic reactions. Like this example shows, this metabolite can transfer, to different metabolites based on the reactions. So all the reaction just, generated a very complex metabolic reaction network in our body. So it means that if we get one reaction pairs from the metabolic reactions, we can see that those 2 metabolites, they have very similar structure. And because we know that the MS spectrum reflects the structure of the metabolite, so it means that they should have the similar MS spectrum, and we just get the MS spectrum of the 2 metabolites, and we can see that they actually have the very similar MS spectrum. So if the metabolite A and metabolite B are in one reaction pair, and metabolite A has a MS spectrum in the standard library, and metabolite B doesn't have the MS in the library. So it means that we can use metabolite A's MS spectrum as metabolite B's surrogate MS spectrum. So it means that we can also notate metabolite B even we don't have the metabolite B's MS structure in the standard library. So according this concept, we can do the mRNA-based recursive metabolic annotation. For example, we have 3 metabolites here, and they can transfer to each other, in that, metabolite A, B, they are in one reaction pair, and B and C, they are also in one reaction pair. So for example, at the first step, we just use a standard library to annotate the metabolite A, and we can use metabolite A's MS spectral as metabolite B's surrogate MS spectral. So we can also annotate metabolite B. Of course, use the same method, we can also annotate metabolite C. And we can see this recursive annotation process. And after the metabolite C, we can do any annotations. So this process just has ends for each. So to do the whole annotation based on the metabolic reaction network, at the first we need to have some metabolic reaction network, right? So we just download the KGD pathway database, and then we get all the reaction pairs from it, and then construct the metabolic reaction network, namely mRNA. And so this mRNA contains around 7 solid metabolites and 9 solid reaction pairs. It's very large network. And so then the mRNA, based recursive metabolite annotation can annotate the metabolite along with the network with recursive ways, like this figure shows. So based on this method, we just developed software. We named it the MetaDNA. The full name is metabolite identification and dysregulated network analysis. And so MetaDNA is a web-based software, like this figure shows. The user can just upload their data, and then they click the start the data processing, and then they can download the results. So to evaluate the annotation result of MetaDNA, we just use a fly metabolomics data as example. Because MetaDNA is a recursive annotation, so we can do that, the meta annotation for each round. We can know the number for each round, and because for the mass spectrometry data, we have positive mode and negative mode. So finally, we get around 2,000 metabolites from the mass spec raw data. And if we use a traditional method, the standard library annotation method for the annotation for the data set, we can only about 500 annotations. So we can do that. MetaDNA can significantly increase annotation metabolite number. So I want to make a brief summary of the second part of the presentation, the bioinformatics method development for mass spectrometry data. The first I developed the TenMass is a comprehensive computational framework for LC-MS-based metabolomics. It's a cross-platform, uniform, shareable, traceable, and reproducible, and it is also very flexible and extensible. So I'm still working on this project to develop new tools for the TenMass. And second is MetaDNA, is the metabolic reaction network-based metabolic annotation. It's the first algorithm, use the metabolic reaction network for recursive metabolic annotation, and it can significantly increase the numbers of annotated metabolites. Okay, so the third part, I will introduce how I use mass spectrometry, metabolomics, and other omics data for precision medicine and the biology questions. So the first about questions that I focus is pregnancy or the woman health pregnancy diseases. We know that healthy pregnancy is very important for women's health, and accurate estimation of the timing of pregnancy or the gestational age and birth is important for many clinical decisions, including the determining of the preterm birth and the repeated treatments. And there are around 10% of the preterm birth, women are preterm birth, and preterm is a leading cause of global neonatal morbidity and mortality. So the current method for determining the genital age, there are 2 methods. The first method is based on the last menstruation date, but this method is imprecise. And the second method is ultrasound imaging, but this method depends on the acceptability at early pregnancy. But there's very easy to missing the time window for the pregnancy, even in the development countries. So we want to know if we can use samples or omics data to predict the gestational age. So we just collaborate with Professor Mads Morberg from Denmark. We constructed a pregnancy cohort with high density sampling, like this figure shows. We recruit 30 pregnant women, and then we collect the blood samples, including the blood samples, original swab samples, and stool samples weekly, almost weekly. And then use the different blood samples. We collected the different metabolomics data. For example, we get the transcriptomics data, we get the proteomics data, metabolic data, and we also get the cytokine data. And for the stool samples and the original swab samples, we get the micro samples from them. And at the meantime, we also have the clinical information from the participant in this cohort, for example, the blood pressure or something, and medication intake, something like that. So this figure just showed, the demographic data of all the participants in this cohort. We can see they have very diverse backgrounds, such as BMI, age, and parentage. So finally, we get a very comprehensive and longitudinal metabolomics pregnancy data set, like this figure shows. And so we get a lot of biosamples. We get a lot of, the different omics data. For example, we have around 17,000 transcripts from the transformative data. It's very, very comprehensive and valuable data set for the pregnancy study. So for this project, at first, we want to know if we can use metabolomics from the blood samples to predict some just age and preterm. So first, we just use metabolomics data to know if they can represent the pregnancy progression. So interesting, like this figure shows, we can detect the metabolomics can represent, all those pregnant samples according to their just age. And what is important or what is interesting that we can see that after the childbirth, we create the postpartum sample, they just come back or go back to the earlier GA samples. And then we want to know what metabolites, just significantly disrupted during human pregnancy. So here we use a SAM test, significance analysis on microarray test to get the significantly disrupted metabolites during human pregnancy. And then we selected 30 increased metabolites and 39 decreased metabolites. And we can tell that most of the increased metabolites, they are steroid hormones, and most of decreased metabolites, they are the lipid or lipid-like metabolites. So next, we use a heat map to show the change of the metabolite during human pregnancy, and we can see very clear patterns of the change of the metabolites during human pregnancy. This is increase and this is decrease. And what is important that because for the cohort we have the postpartum samples, namely after the child delivery samples, and we can see that for the metabolite that increase during human pregnancy, and they just significantly decreased, come back to the baseline after the child delivery, like this of last column shows. And of course, for the decreased, they just increase after the child delivery. So next, we want to know if we can use the metabolic data from blood sample to construct different models and to predict the gestation age of pregnant women. So here we just use a discovery cohort. We divided our data set to discovery data set and the one data set. And use a discovery cohort, we just use a lasso, and then we get set of features from all the metabolites. And then we have two independent data sets, test 1 and test 2. And for the test set 2, they are totally independent cohort from this cohort. And finally, we selected the 5 metabolites that can be used for the prediction model construction. And so this is a prediction result for the discovery data set, and we can see that they have very good prediction results. R-squared is about 0.85, and we also get a good result, a prediction result for the test set 1. The R-squared is about 0.8. And we also use the very independent test set 2 to validate or confirm our prediction model. And we can see that we also get a very good prediction results. The R-squared is about 0.83. So here I just want to show that for the metabolite annotation in this project, I just used the med ID from the TenMass, and this is example of the 3 biomarkers we found, and we just use med ID to notice the metabolite. And what's important that because this is a longitudinal cohort for each person, right? So we can also see the prediction result for each person here. So we can do that. So for each person, we also get a very prediction result using prediction models. We constructed with the 5 metabolites. And of course, we also get a good prediction result for everyone in the validation data set. Okay, so you can see that for this project, we just use the blood samples, right? Because blood sample is very common and widely used for biomarker discovery and diagnosis. This is because the blood samples contains more biological informations, and of course it also contains a lot of metabolites, and the blood samples are also very robust. So this is why a lot of studies and that is diagnosis use blood samples. But sometimes the blood samples have some disadvantages. It's invasive, right? It's painful to collect the samples. So, and it's also very complex to collect the blood samples. You need the doctor or the nurse help to get the samples. So, but for the urine sample is non-invasive and is simple and flexible. You can just collect the samples by yourself. And of course, urine samples also collect a lot of metabolites. So we want to know if we can also use the urine sample, urine metabolic data to predict the gestation age more quickly and flexibility. We do that because for the developing countries in the Africa or Asian, there's a lot of they don't have very good clinical environment, so the urine samples may be more flexible than the blood samples. So we collaborated with UCSF, Dr. Prof. Larry Rance. We constructed another pregnancy cohort with high density urine sampling, like this burger shoes. We just recruited 36 participants, and then we also, for each participant in this cohort, we collected the urine samples almost weekly. And then we use the urine sample to collect the metabolic data. So next, at first, we also want to know if the metabolic data from urine samples can represent or reflect the pregnancy progressions of the pregnant women. So here we can see that in the PC score plot, we can see that the sample is just ordered by the gestation age. And what is important, like the blood samples, the postpartum samples also combined with the earlier GA samples. So in that, the metabolic data from urine samples can also reflect the pregnancy progression of the pregnant women. So next, we want to find the dysregulated metabolic features during pregnancy in the urine samples. So here we also use the SAM test, and we get a lot of dysregulated metabolic features during pregnancy. And use these dysregulated metabolic features, we also constructed a heat map, and here we use K-means clustering. And we can do that all the samples can divided into 3 different clusters, and the clusters are ordered by the GA of the samples. And what is important, we also see that the postpartum samples combine to the earlier GA range of the pregnant women. So next, we want to know, because this is a longitudinal cohort, right? We want to know at a different stage of the pregnancy if the dysregulated metabolic numbers gradually increased. So here we just divided all the samples into different GA range, and then we compare them to the baseline. Here baseline we define is a 10-week to 16-week, and we can see that the dysregulated metabolic feature number just increase according to the GA, and it's very clear pattern. And what's important that after the childbirth or the postpartum, you can see that the dysregulated metabolic number just decrease. So next, we want to know what the functional or what pathways to dysregulate the urine metabolic state. So here we just do coordinate network, and then we get the network. And next, we just want to know what modules in network. So we just communicate analysis, and we just find the different modules or communities in this network. And we can detect cluster 2 here is the biggest network or the modules in this network. And we just get a zoom in this network, and we can see that it contains a lot of different metabolites. And then next, we just combine all the metabolites in this network in cluster 2, and we can see the change during human pregnancy of this cluster. And we can see this cluster just increase during human pregnancy, and after childbirth, it just significantly decreased. And so then we just do the pathway enrichment for this cluster, and we found that most enriched pathway in this cluster is a steroid hormone pathway, which is consistent with our research in the blood samples. And then we just do all the pathway enrichment for all the metabolites. We found dysregulated metabolites, and we found about I think 30 pathways here. And here we just this is number of the pathway in these pathways. And then we just, we just find the pathway that they are consistent for the change in the pathway level and in the metabolite levels. And then we just find 6 pathways here. And we just show here, this is metabolite levels. And we can see for the metabolites, you can see every metabolite in this pathway just increase during human pregnancy. And we also show the pathway changing in the pathway levels uses a regular plot, and we can see that this pathway just increase during human pregnancy and after childbirth, just come back to the baseline. So next, of course, we want to know if we can use a metabolite from the urine samples constructed predictive models to predict the gestational age of the pregnant woman. So here we use the random forest models, and we finally we selected 21 metabolites, like this figure shows, and then we use 21 metabolite to construct different models, and then we divided the data set into discovery data set and what data set, and then we can do that we can also get a very good predictive result for the gestational age of the woman. And we can do that for the discovery data set is just ask squares about 0.8, and what it said is about 0.99. So of course, for each one, we also get a good predictive result. So like this figure shows. And next, we want to know if we can predict the time to delivery. So the time to delivery define that the sample collection date or the time and to the delivery time. So here we also use the same method with a random forest, and we also get about 21 metabolite for this predictive model. And we see the overlap between this metabolite set and the predictive models for the gestational age. And then we can see that they have a lot of overlap, about 18 metabolites. They are in the 2 predictive models. And so we get 24 metabolite in total. Of course, for the prediction of time to delivery, we also get a very good predictive result, like this figure shows. For this discovery data set, we get about 0.89, and for the validated data set, the adjusted R square is about 0.77. And then we divided, the metabolite 24 markers into 2 groups using the class method, and we can see very clear that one class of the metabolite just decreased during human pregnancy, and another just increased during human pregnancy. And we also use a plot to show the change of the metabolites. And one of the metabolite in the decrease is CAMP, and this is signal metabolites. And another metabolite in the increased metabolite is the progesterone. This is a hormone, and this is also consistent with our finding from the blood samples. Okay, so I want to give a brief summary of the women health studies. So the first is that we use the first is blood metabolomics could be used to predict gestational age. And for this project, we constructed a metabolomics pregnancy cohort with high density sampling. And we get a lot of biological samples, including the blood, vaginal swab, and stool samples, and we get a lot of metabolomics data from it. And we use metabolomics to add further to demonstrate that we can use 5 blood metabolites to predict gestational age. And for the second project about the urine metabolomics to predict the gestational age, we constructed a pregnancy cohort with high density urine sampling. And we also find that we can use the 21 metabolite to construct the predictive models. And this model can be used to predict the gestational age of pregnant woman. Okay, so next we can see that just like I mentioned about that blood is one of the most important biological samples for biomarker discovery and diagnosis. And but for the traditional blood collections, this method, the intravenous blood sampling, we know it's massive, and so we need the clinic help. We can't collect the blood samples by ourselves, and it's a high sample volume needed. So for the precision medicine we need a high frequency sampling, right? So it's obvious that this method can be used for the high frequency sampling for personalized health monitoring. So we just want to know if you can use the micro sampling to do the same thing. So because for the micro sampling, like this figure shows, it's less painful and it is very easy and flexible, and so we only need a small sample volume. So next, I just developed a platform. I call it metabolomics microsampling, and we use this method for the pre-medicine study. So based on the microsampling, we just developed a workflow of microsampling metabolomics platform, like this figure shows. After we get the micro samples from microsample devices, then we prepare the sample, and then we use different instruments to collect the different omics data. Here we collected the lipidomics, metabolomics, and protein data. And we also get the cytokines and hormones using the targeted assay. And after we get data, we do the data processing and use the data for the different studies, pre-medicine or the pre-nutrition or the biomarker discovery, something like that. So here you can do that with mass spectrometry, because mass spectrometry is very and high sensitive, and it can be used, widely used in the field, and it can be used to detect the low abundance metabolite molecules from blood samples. So to demonstrate that this method can be used for the precision medicine or the precision nutrition, here we perform 2 case studies. The first one is metabolic phenotyping response to ensured sugar consumption. So here we just recruit 32 participants and let the participants drink the ensured shake. And then we just collected the micro samples after participant drink the ensured shake, and for different time points. Of course, we also collected the baseline before the participant drink the ensured shake. So for each participant, we get 5 time point samples for them. And then we just get the dysregulated molecules after the people drinking the shake, and then we divided the molecules into different clusters here. So you can see that we get 3 different clusters, cluster 1, 2, and 3, and they have different patterns after people drink their shake. For example, for cluster 1, we get that the molecules just increase very quickly after people drink their shake, and they have a peak around 60 minutes and then come back to the baseline around 240 minutes. And cluster 2, you can that it also increase after people drink the ensured shake, but you can see compared to the cluster 1, the increase is gradually compared to the cluster 1, and then come back to the baseline. But we can that they didn't come back to the baseline around 240 minutes. And cluster 3 just decrease after people drink the shake and increase. So they have different patterns. So let's see from the the examples of the different class of the molecules changed during after people drink the ensured shake. The first one is amino acid. We detected some of the amino acid from the metabolomics data from microsamples, and we can see that those amino acid they are all in the cluster 1. They increase on the drinking the shake and decrease. And the second one is carbohydrates. This metabolites just increase and decrease because they are also in cluster 1. They all make sense because the carbohydrates are the ingredient of the ensured shake, right? So they should increase after people drink their shake. And so in summary, this result demonstrates that the kinetic case of the biochemical response to ensured shake can be revealed using the metabolomics data from microsamples. So because we have so different metabolomics data from the microsamples, so we want to know if we can use this data set data for the quantify people's response to different nutritions. So we just construct the metabolic response based on different class of the molecules. So for example, finally, we get 6 metabolic scores here. The first one is carbohydrate score. We use all the carbohydrate metabolites. The second one is fat score, and the third one is amino score. We also have the insulin excretion score, free fat acid score, and because we also have the cytokines in the micro samples, so we also get the inflammatory response scores for each one. So finally, we can get 6 metabolic scores for each one. So here we will read a plot which shows the people's response to different nutrients here. We can get an example is group 1. So here, for example, we did this guy has very low carbohydrate score and fat score. So this is more important for the pre-nutrition. So from this, we can know that these people maybe avoid some food, right? So maybe some for other people, they should eat more of this food. So this is very, very important for the pre-nutrition in the future. So the second case study is about, we call it the 24/7 project, because for this project, we want to know if we can use metabolomics data from microsamples for the precision medicine. So here we recruit 1 participant, and this participant just collected the microsample almost hourly, and we And finally, we get 98 microsamples over 7 days and use the microsamples for the metabolomics data acquisition. And we also use wearable devices to collect the wearable data. Here we use a Fitbit to get the heart rate, step, sleep, and we use the Dexamon to get the continuous glucose from blood samples. So we can do that. So we get a very, very comprehensive data set for this person, 24 hours over 10 days, including the wearable data and the metabolic data. So first, we want to know if this metabolic data from the microsamples can reflect the people's health status. So we know, because we also have the food log data for these participants. So we know these people just drink the milk every morning around 7:30. So we also detected 2 metabolites. They are the ingredients of the milk. And we can see they are very clear link between the food log data and the metabolic data from microsamples. And we also detected the one drug from the metabolic data from the microsamples. And we can do that. So they also has very clear, patterns. We also know this drug stay in this human bodies around 24 hours. So now we have very high density, metabolic data for this person. So we want to know if we can do the circadian rhythms analysis for the molecules. And we just discovered a lot of molecules that they have very clear circadian rhythms. So for example, we divided the molecules into different modules. Here we get 3 modules. For example, for the module 1, you have very clear patterns, the very low at day and very high at night. And we also see that most of the molecules in the different modules, they are lipids. So because, we have the high dense metabolomics data here. So because, for the wearable data, they very high, these are high frequent, right? So now because of the high frequent of the metabolomics data here, we can do the correlation between them. And here we use lect correlation. We develop the lect correlation, so we can get the causal relationship between them. So we get a network between the wearables and the metabolic data here, like this figure shows. And then we focus on the glucose network, and we found very interesting, the causal relationship between the wearable and the metabolic data. We can give one example: it's the CGM, it's glucose, and alpha-synuclein. Because there are some studies show that the alpha-synuclein can increase the glucose in the blood samples, but we don't know the time window between that. So here, based on the method and the data set we have, we can see that it's about 50 minutes. So it means that alpha-synuclein increase, and after about 50 minutes, the glucose increase in the blood samples. So this method is very useful. Maybe in the future, we can use this method to do the causal relationship between the different time series state. So I want to give a summary about this microcellular metabolomics. We constructed this method fully remote, scalable, and high temporal resolution omics and sensor monitoring. And it has a potential for large-scale comprehensive dynamic molecular and digital biomarkers discovery and monitoring, as well as health profiling. And we also developed new algorithms can be used to discover potential causal relationship between the 2 time series state. And to integrate the high-frequent microsampling metabolic data and wearable data, we can achieve personalized health monitoring and this diagnosis in the future. Okay, so next I want to talk about is, for the metabolomics, one of the most important application of metabolomics is biomarker discovery diagnosis. And this figure just shows, the traditional workflow for the biomarker discovery and diagnosis using metabolomics. We get the raw data. We need to do a lot of things, data processing and data cleaning for it. And then we can get the biomarkers, control the models. But we know, just I mentioned about, for the traditional metabolomics, we have 2 limitations for it. The first one is formation loss, because, feature detection is not perfect. And there's a lot of features have no annotations. And the second one is batch effect. So because, during the data acquisition, we have a lot of batch effects, and sometimes alignment is wrong. So we have a lot of batch effect in the data set. So can we overcome those limitations for the metabolic data for the biomarker discovery diagnosis? Can we just skip all the steps for the data processing and just use the raw data for the predictive model and the diagnosis? So this is the last method, the last project I want to talk is a deep learning-based cytomass spectrometry image analysis of property medicine. If we look at the mass spectrum raw data, like this figure shows a 3-dimensional data set, x-axis is reading time, y-axis is accurate mass, and intensity is z is intensity. So if I just convert the mass raw data to image, I call it metabolic image or the CytoMS image, and you can do that. It's also a three-dimensional image, and we use a color to represent the intensity of the data point. And the advantage of this method that all the information is in the CytoMS image, because we just convert the raw MS image to the image, so it contains all the information from the raw data. And the second advantage of this method is that it can handle the batch data, because if we see the raw data as an image of cat, like this figure shows, right? So the reading time shift for the mass spectrometry is just like the shift the image to the right, and the accurate mass shift is just like the y-axis go up, and intensity shift is just like just like the intensity, the image just become lighter or darker of the image, right? So, but we still know they are cats, right? So because the profile is still there. So based on this concept, I just developed the DeepSide MSI project, and this project contains two parts. The first part is CytoMS image converter. This product used to convert the MS raw data to the image. And the second part is image predictor. So here, because deep learning is very powerful tools for the image processing. So here, just use a deep learning to process images, send to MS image, and construct the predict models. And then if we get the new samples, we can just put the samples into the predict model, so we can know if it is all healthy. So here, I just want to know if we can use this method for the diagnosis. So here, just use pregnancy cohort I mentioned about, and you can do that. We can get the good predictive result using this method, and we can also get the good predictive result for each one in this cohort. So to confirm and validate the DeepSide MSI, we also download two public datasets. And then we use DeepSide MSI to process them. And those two datasets are the cancer dataset, and so we can do that. We can also get very good predictive results for them. Both of them. The first one is about accuracy about the 97.7%, and the second one is about 87.8%. Okay, so the last part is a future plan. I want to give a very brief future plan on my research. And the first project I want to do in the future is still the DeepSide MSI improvement. Just like I mentioned, DeepSide MSI I think is very new and very great algorithm to process the LC-MS raw data for this analysis, but it still contains a lot of disadvantages in this project. I call it version 1. So in the future, I want to improvement of this DeepSide MSI algorithms. For example, now for the DeepSide MSI, we only have one date to convert it to the image. But for the mass spectrometry, we have the different mode for the one sample. So next, I want to combine different data from one sample as one image, so we can contain more informations. And I can also use a different deep learning method, because now for the version 1, we use very simple deep learning method for the image processing. In the future, we can try to do different, because there's a lot of new method for the deep learning for the image processing. So in the future, I can try to do different deep learning method to process images. And the aim 2 of this project is that I want this method can be used for the clinic. So I want to construct it online or offline diagnosis system for specific diseases. So here, of course, is pregnancy. So to do this, I need to collect the different, the cohort from other hospitals or other centers. So of course, I can also download the public dataset, other people publish it. Then we can have the more dataset, and then construct more robust prediction models for disease diagnosis. Okay, the second project is I want to do the metabolic future-based metabolic model detection during pregnancy. I want to do that because, just I mentioned about that metabolic annotation is very difficult. So it means that now there's a lot of people, they study how the metabolic change during human pregnancy, but we didn't get overall of the metabolic change during human pregnancy. So to do that, the first part or first aim of this project is master development. I just want to develop metabolic future-based metabolic module detection algorithms. So I just download. To do that, we need to choose a database. We need the metabolic network database. We need the compound database. And now I just get the metabolic network from public dataset. I download them up to the public dataset, and I think it's as far as I know, this is the largest or biggest metabolic network in this field. And I also download a lot of compound database, and now we have around 100,000 compounds in the database. And what is important that most of the compound in this database we have the MSMF for it. Okay, so and after that, we just get the cluster or the patterns for different features, and then we map the features into the metabolic network. And then we can use computer analysis to get modules from the network. And then we can know what metabolic module or pathway change during pregnancy. So we can go get an overview overall of the metabolic change during human pregnancy. So this is project 2. Now, project 3 is molecular phenotype of response to human pregnancy. Just as I mentioned about, we have the comprehensive and longitudinal metabolomics pregnancy cohorts, and we have the different metabolomics. And now we just published and finished the metabolomics part. So next, I just want to continue this project. And the first one that we have some microbiome data here, right? So I just want to develop a new method to get the microbiome and the metabolite interaction between the metabolite and the microbiome, because microbiome affect human health through the metabolites. So I want to give an overall interaction between them. And the second aim is that I want to know how the molecules and the microbiome change during human pregnancy. So maybe we can know about the physiology of the pregnancy, so we can give more things about the pregnancy. And the second aim is that the dynamic of intramolecular and the microbiome network during human pregnancy, because we know that different molecules, they have very interactions between them, right? So because we have so many metabolic data, so I want to explore the interaction network between them in the future. Okay, so I will give a summary of my research. My research, I think, the first one is master demand, just I mentioned, especially for the mass spectrometry data, metabolomics, proteomics, and lipidomics. Of course, I'm also working on some project about the data interaction, especially with microbiome and metabolite interaction, and also working on some wearable and omics interaction. And for the biological mechanism and precision medicine, I will focus on the woman health, especially the pregnancy and pregnancy-related diseases. And I'm also interested in the personalized health monitoring, and I'm also working on some project about the aging. Okay, so at last, I want to thank my postdoctoral advisor, Dr. Michael Snyder. Without his support and help, most of the project studies I present today is impossible. And I also want to thank my PhD advisor, Professor Zhang Zhu. He teach me a lot of things about the metabolic state process and analysis. And of course, my collaborator, Professor Caroline Johnson from Yale University. She helped me a lot in the TenMass project. Of course, I would like to all the the people's collaborators from Standard Lab and Stanford and Yale. And of course, I also need to thank the fundings from NIH. Okay, that's all. Thank you so much, and I'm happy to take any questions if you have. Thank you.
All right. Are there any questions right off the bat? It looks like Jane has a question.
Hi, my name's Jane Roosh, and I am clinically a diabetologist.
Mm-hmm.
And I was very interested. Well, first, I just want to thank you for a tour de force of a talk. It was very impressive. And I was intrigued by the profiles post a mixed meal tolerance test that you gave. And if you had any thoughts about putting those together with the behavioral remote monitoring and how changing behavior might change those profiles or identifying high-risk profiles?
Oh, you mean the metabolomics, microsample metabolomics and the wearable data, right? Yeah. So now for this project, now we only have the wearable data that from the smartwatch and glucose, right? So yes, it's a great idea that maybe in the future we can add more wearable devices to have the different the wearable data. But now I have no idea because I only focus on, I think I'm more focused on the metabolomics data from microsamples, and if we can use this metabolomics, always integrated with wearable data for the pre-medicine. So now I have no idea how to use this for the other wearable devices. Yeah.
So maybe to reframe, but in the sequential metabolomics data after a mixed meal challenge, can you see using those data pre and post an intervention, whether it was pregnancy, whether it was exercise, whether it was diet and weight loss, in terms of predictive modeling based on your algorithms?
Yeah, I think so, because for this one we can try to use this for this, because how to say, so we have the different omics data, right? Especially metabolic data and other omics data. Yeah, so we can use this other omics data, use the same method to do the data protein analysis to construct the models for the pregnancy or other diseases. Yeah. Yeah, thank you.
I had a quick question if there's still availability. So I was interested in your deep learning model, and I was wondering two parts. First, can it work for different types of data acquisition? So like swath MS or data dependent or data independent acquisition? And then secondly, can it distinguish between different types of protein isoforms or modifications?
Yeah, these great questions. Yeah, so for the first question, you mean if we can use other different, because for this one we only use the MS1, right? With acronyms, we don't have MS spectra. I think we can use DIA because just because deep cytoanalysis, this project only requires that you have the MS1 or intensity information for the futures, right? So I didn't do that because now I just do the genomics data and the metabolic data, and they are all MS1. But I think it should be work for the DIA data set. Yeah, I think we can try to in the future, because I'm still working on it, so I can try to see if we can use the DIA data to do the same analysis. And for the second, I'm sorry, can you repeat your second question?
Yeah, can it distinguish between different protein isoforms or modifications?
I don't think deep cytoanalysis can do that, because deep cytoanalysis, I do this I only want this can be used for the disease diagnosis. So now it's still a black box. It can't be used for the for other things, for the biological studies, right? So it only can be used for the disease diagnosis. So in that we don't know what they are. We just put all the data into the image and put the predictive model, so we know they are diseases or healthies, but we can't use this for any other biological studies. Yeah, thank you.
All right. So it looks like we're actually at time here. So if we have more questions, we can ask you tomorrow.
Yeah, sure. Thank you so much.
Thank you so much for an excellent talk. I really enjoyed it.
Yeah, thank you, everyone. Bye-bye. See you.